Hello, Stats fans. How are we doing today? Hope all is going well. Hope everybody had a good weekend. Hope you're staying safe. Hope everybody within your family is doing okay. Um, Once again, if you have any questions on anything that we're doing, please feel free to email me. Um, I check my emails and I respond back to emails or any comments that you have on Progress Book or on Google Classroom. That would be great. If things aren't going well for you in regards to this type of delivery, please email me any type of concerns that you have. We need to continue through this though because we are dealing with the University of Findlay. University of Findlay is also continuing in this type of manner. So they're going to expect us to be able to finish out the material that we're going to need to finish out. So we will continue through. What you will need still today is your Z table. We will still be utilizing this, and hopefully you've kept up with the work that I've given to you. I've tried to make it not very taxing for you in regards to it, but we still need to once again get through the material. Once again, if you do have concerns or anything that's coming up that you're having problems with, please email me or message me, comment me through the Google Classroom. Today will be the last section of this chapter, and we'll start reviewing the chapter. The last section of this chapter is called the central limit theorem, and dealing with the central limit theorem. What we start doing now is we start taking groups of people. We've talked about the concept of if we wanted to take the average height of males age 18 in the state of Ohio. Different processes that we could do to do that. Well, another process that we can do is we could take a look at each school district. Each school district, choose 20, choose 30 kids, 18-year-olds at random, and find one mean, one value of those 30 kids. Rather than having 30 data points, we just have one data point, which would be a sample mean, or 40 values that you choose at random, and you just calculate what the average mean is of that. Well, that's what the central limit theorem deals with today. When we have a sampling distribution of sampling means, and once again, you can follow along with the notes that are posted on Google Classroom. I posted the notes that you can follow along. And if I do go too fast, once again, how do we solve that problem? If I go too fast, hit your pause button. I promise I won't continue to talk. And then when you catch up to what we need to, hit the play button again, and we take off again, all right? See, that's the advantage that you have, because in the classroom, if I start going too fast in the classroom and I don't have the pause in there, you just continue to fall behind. See, now you can hit a pause button. There is a chance for you to just shut me up. You just hit pause. Okay, sampling distribution of sampling means. A distribution using the means computed from all possible random samples of a specific size taken from the population. And I made speed through things a little bit, and that will make my YouTube video a little bit shorter, which helps out with respect to downloading. So I may go through this a little bit faster, so I will not be offended if you have to hit your pause button. I won't be offended at all. Okay, but I'm trying to shorten the length of the YouTube video also by going a little bit quicker in the pace. So we have a sampling distribution using the sample means computed from all possible random samples of a specific size taken from the population. That would be taking 30 18-year-olds from each school district in the state of Ohio and calculating one mean. And then we're going to do a sampling distribution of just all the means. So we can find the mean of the means and the standard deviation of all those means. That's what this is right here. We're trying to find a sampling distribution for all the means. And once again, this is just what we have talked about before. All average males age 16 to 18. We just take 30 at random from each school and calculate the mean. calculate the mean of the 30 males or 40 males from each school, and we get one value. So rather than dealing with 30 times 800, which is 2,400 data value points, we're going to be just dealing with 800 data points, which is sort of nice. Standard error. The difference between the sample measure and the corresponding population mean due to the fact that sample is not a perfect representation of the population. Okay? We take all these samples and we take the mean of all these means. The difference between the actual population mean and this sample mean of means, that's your standard error. And by the way, just as a side note, if you've watched any news on the coronavirus, a lot of the charts that they're dealing with, okay, they're talking about lowering the curve and lowering the curve down. There's a lot of bell-shaped curves that are going through this. They want to talk about flattening the curve. What they're trying to do is they're trying to get this to not peak as high. And once again, that is a standard normal distribution. So your z-values and what we've been talking about, your bell-shaped curves, a lot of your graphs that you see, the flattening of the curve is those z-values in the z-curve. Properties of a distribution of sampling means. The properties. The mean of the sample is equal to the mean of the population. That's what we hope for. That's what we hope for. The mean of the sample turns into the mean of the population. The standard deviation of the sample means will be smaller than the standard deviation of the population. Okay, the sample means standard deviation will be smaller than the population standard deviation. So it's going to be a little bit different there. Now, this here is your standard deviation of the sample means. And we signify this by a subscript. We have the sigma there, that's mean standard deviation, and then we had x bar. Okay, so that's the standard deviation of the sample means. So how we can calculate this is your population standard deviation divided by the square root of n. Now this n is sample size. This is your sample size. This is your population standard deviation. So this is your population standard deviation. Once again, the standard deviation of the sample means will be smaller, and how we calculate that is we take the population standard deviation divided by the square root of n. And this is the mean of the sample means. When I talk about mu with a little subscript x, and I can put a little bar there if I wanted to, it just means the mean of the sample means. So if I would take all these averages, okay, all these means that we calculated, the males, 30 males, we calculate the mean of these 30 males, okay, and then we take the mean of the means. That's what this value is. That's what this value is, the mean of the means, and this is the standard deviation of all those means. Central limit theorem. Once again, you can click pause. If you click pause, okay, you can write this down as we go through. As the sample size increases without limit, the shape of the distribution of the sample means taken with the replacement from the population with a mean of mu and a standard deviation of sigma will approach a normal distribution. So what in translation, what this means is this will start to become normal. If I take the mean of the means and the standard deviation of the means, this will approach a normal bell-shaped curve. So we can use our z-values to deal with this also. Once again, if you need time to write that down, just push pause. How we calculate a z-value, because this all goes back to a z-value and a z-table. This is your sample mean minus our population mean. Get this out of the way. This is our sample mean, the mean of the means, and the mean of the population divided by square root of the standard deviation divided by the square root of n, which this should be an x bar there. This should be an x bar. And we could do this when gathering information about the sample means. How we calculated our z-value before was value minus the mean divided by the standard deviation. Now what this is replaced by is this is the sample mean, this is the population mean, and this is the standard deviation of the sample means. So we have x bar minus mean divided by a sample of standard deviation. When we're dealing with just one single value, when we're gathering information about the population, I should eliminate this. You can get that x bar out of there. We just have x, our value minus mean divided by standard deviation. Okay, so that's what we've done up till now. This is what we did till now. This is what we're going into. This is when you're dealing with a group where you're talking about the sample means. Okay, we're talking about the sample, a sample size, and you're doing the means of the means. This is what we're utilizing. When you're just talking about one single value that we did last week, this is what we're dealing with. Key ideas from a central limit theorem. When the original variable is normally distributed, then the mean of the sample means will be normally distributed. That's what's going to be given. Okay, when I have the mean, when I take the mean of the means, okay, and I deal with a normal distribution, which was, or my values that were normally distributed before, the mean of the means will be normal distribution also. When the distribution of the variable might not be normal, the sample size of 30 or more is needed to assume, or needed to use a normal distribution approximate the sample means. The larger the sample, the better. Once again, won't feel offended if you have to push pause. Now, what this talks about here, the larger the sample, the better. What are we talking about there that we've dealt with before? Which law was that? Let me think about that for a second. We dealt with the law, especially when we were dealing with the M&M lab. What law was it? That's exactly correct. This here is the law of large numbers. And that's what the government's trying to do right now with the coronavirus. They're trying to get sample sizes that are large enough so they can start making predictions then. They're using a lot of statistical analysis sitting there trying to predict out with respect to the coronavirus. Okay, they're trying to use that data that we have right now to be able to do that. And the more sample and the more days that go by, the more samples they can get, the sample size continues to grow, and then it can predict out what's going to happen with a pretty good confidence. Let's look at some examples. The mean weight of 15-year-old males is 142 pounds. Standard deviation of 12.3 pounds. If a sample of 36 15-year-old males is selected, find the probability that the mean is greater than 144.5. Assume the distribution is normal. So what this turns into now is, if we take a look, we have the mean weight, which is your mu, of 142 pounds. The standard deviation is 12.3 pounds. Now we are choosing a sample of 36, so our n value is 36. We want to know the probability that this mean, so we need the probability that this mean of the sample that we're dealing with is going to be greater than 144.5 pounds. That's what we're trying to collect or predict. Now, what you'll see in this is only thing is different is how we calculate our z-value. From that point on, everything's going to look the same. So we're going to calculate a z-value for 145. I'm sorry, 144.5. So how we calculate our z-value now is we have x bar minus mu divided by standard deviation divided by the square root of n. Okay, that changes just a little bit. Before, it's just the standard deviation, because we are only dealing with one person. So if you want to think about it this way, when you're just dealing with one like we had last week, we just had one. Square root of 1 is the value of 1. The average of one person is that one person. So this just reduces back to what we did for the z-value last week. So we have 142, 144.5 minus 142 divided by our standard deviation, which is 12.3, divided by the square root of 36. Now this becomes a calculator exercise for you at this point. Here's my suggestion. Take the top two, calculate that value. So we have 144.5, 144.5 minus 142, and hit enter. Calculate that value. Then divide by, tartar sauce. Let's do that one more time. So I have 144.5 minus 142, hit enter, get your 2.5, hit your divide by, that pulls your answer down, and then quantify the bottom. 12.3 divided by second square root of 36, and close both those parentheses out. Because we had a parenthesis here, we had to close that out. The square root gave you a parenthesis also. And what you should come down to is 1.22. Once again, take it out 2 decimal places. So our z value is 1.22. I think it was. Yep, 1.22. Now we go back to what we did last week. Draw a normal bell-shaped curve. Okay, this should look very familiar. We have our value here, which is our mean. Our value here, which is our z-value. Here's our 0 value, We want to figure out the value, the amount that's greater than, the probability that we are greater than, so we're trying to calculate this area. Now we go to our z-value, our z-table. If you remember, our z-table gives us the area from 0 to a z-value. So we have 1.22. So look in your z-table. Should come down to 0.3888. And then the question is how do I find this area out here? Because that's the area we're trying to find. Now if you remember, from here to here, this area is 0.5. We subtracted off the 0.5 minus the 0.3888. So this area that we were calculating is 0.1112. So if I want to put it into a percent, this is fine here. Or we have 11.12% chance that if I take a sample of 36 15-year-olds, there's 11.2% chance that my probability or that my weight's going to be greater than 144.5 pounds. Once again, predictability. Second example deals with bacon. Bacon, 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 bacon! We get some bacon here. Everybody's going to be hungry for some breakfast now. Okay, get some breakfast. The average slice of a pound of bacon, sliced bacon, is $2.02. Now, who would do a study on this? I don't know, but they did it. Assume the standard deviation is 8 cents. Random sample of 41 pound packages is selected. Find the probability the mean sample will be less than $2. So we have mu is equal to $2.02. We have a standard deviation, sigma, 0.08. We have a sample size of n is equal to 40. And we want to determine probability that we will be less than, that this x bar is going to be less than $2. Now, what I suggest you do is follow along, okay? Follow along the problem we just did up above, okay? I want you to do that. So I want you to hit pause right now. Hit pause right now and see if you can follow along with what we just did up above on the previous problem. Okay, and then come back and check your solution. Okay, rather than just copy down what I say and what I do up here, hit your pause button, try to work the problem out, come back and check your answer. Let's see if you can do that. I'm going to continue on. Hit pause now, do the problem. So what we have here is, once again, our z value for the $2 is equal to x bar minus mu divided by standard deviation, square root of n. So we have $2 minus $2.02, standard deviation of 0.08. And then we have the square root of 40. So once again, do the top in your calculator. So we should come down to 2 minus 2.02, get negative 0.02. We're going to divide by quantity, 0.08, divided by second square root of 40, 2 parentheses at the end, negative 1.58. as our z value. Okay, hopefully the next step you did, you went to a bell-shaped curve. Oh, darn it. Put your values in, put your zero in. We have negative 1.58. Next step is you go to your z table, you look up your negative 1.58, 58.4429, and we want to determine if we're going to be less than that, so we want this area right here. Once again, we can take our 0.5 and minus the 0.4429. .0571. So there is a 5.71% chance that the mean of these 40 is going to be less than $2. Okay, that's not a very good, and we're only talking about 2 pennies there. Not a very high probability that the mean of these 40 is going to be less than $2. Okay, not a very good chance. Now, if I decrease my sample size, here, what that's going to do is that's going to increase my probabilities, because law of large numbers, I'm not going to be as certain. Okay, I posted some homework problems for you to do. Posted solutions to the homework problems. Once again, keep up with the material for Stark State, or not, Findlay, University of Findlay. Keep up with the material that we have. If you have questions, please email me your questions. I will go over them the next day in a video. Hopefully we're going to get back into a routine here. We had to take a little hiatus here. The custodians did an outstanding job of making sure that our school is clean, hence the rubber gloves. So hopefully we will continue to get a process going here, and hopefully by the end of this week we'll be able to get a quiz over this material. This is the last of the new material. From this point on, it will just be review sheets of this chapter, extra practice problems that you have. Solutions have been posted for you. Once again, if you have questions, feel free to email me these questions or post a comment on Google Classroom. If you're having issues, also please email me that you're having issues in regards to this material, or getting access to this material. Please keep up with the material. Please stay safe. Once again, hopefully you got some Double D ice cream over the weekend. Hopefully it's going to get warmer this week. We'll keep our fingers crossed on that. Stay safe. I miss you guys. I wish we were back to normalcy, but we're not there, so it is what it is. I miss not having you in the classroom. I miss not being a part of your life on an educational basis, on a daily basis here. So keep your social distancing. Make sure you keep yourself apart from other people so we don't pass anything along. The more we do that, the quicker we can get back to normal. And that's what ultimately we want to be able to do, is get back to normal. Once again, if you have questions, feel free to email me. If you don't have anything else, adios. You folks have a good day.